Hey everybody, welcome to mathematics. This is college algebra, math 35 at College of the Sequoias. I'm going to be working on exponents and radicals. This is a review section. It's sections R6 and R7. They go together really well. So that's what we're going to work on here, R6 and R7. This is on exponents and radicals and their relationship. And to make this easier for anyone that's re-watching this after watching it later, I'm going to put a summary of a bunch of the rules on page 1. Then over the next hour or so, I'll explain how we come up with them and how we use them and stuff like that. But here's a summary list of rules for exponents. For exponents and radicals. So we've seen some of these already. We've got a to the m power times a to the n power. That's a to the m plus n power. We can do a to the m power and raise that to the n power, and we get a to the m times n power. We can do our division rules. We could do a to the m over a to the n, and that's a to the m minus n power. Some things that we have that we can distribute with. We have, let's see, let's go with a to the m b to the n. I'm going to raise that to the p power. This is a to the m times p, b to the n times p. And this rule applies to division as well. So I could have a to the m, b to the n, raised to the p power, and this is a to the mp over b to the np. We take a look at some negative values and some fractions. We have a to the negative n equals 1 over a to the n, and as well as a to the, let's do 1 over a to the negative n equals a to the n. So exponents, negative exponents, flip to the other side. Move terms with negative exponents to other side. And make them positive. And one that tends to get often overlooked, we've got, we can call that rule 5 or rule 6. Rule 7 is a simple one. Anything to the 0 power is 1. Okay. We have fractions. We can do fractions and exponents. A to the 1 over n is the nth root of a. This is how they connect to radicals. And it's really like a to the first. Generally, we don't leave in the first, but it kind of illustrates the next rule. And the next rule is if we have a fractional exponent with something besides 1 on top. This is the nth root of a to the m. We could also write this as the nth root of a to the mth power. This is kind of like writing, in terms of fractional exponents, a to the m raised to the 1 over nth power. And this is like writing a to the 1 over n raised to the mth power. And these are all equal. And it has to do with the way fractions multiply, and then their relationship with radicals. So I'll pause that for a second and let you write them down, and then we're going to work over where do we come up with all these and how do we use them. Okay. I'll assume you paused it and you're ready to go. Well, starting off with the 0 one, we have x to the n times x to the negative n. That's x to the n plus negative n, which is x to the 0. And now I could rewrite this as x to the n times, recall I said you could move negative exponents to the bottom. And when we multiply these, this is x to the n. You can make that a denominator of 1 and multiply the fractions. But anything divided by itself is 1. And these two things are identical. So x to the 0 equals 1. And I didn't say what x is, so anything works. Let's see, pause this for a second. And I don't know if that was the best spot to start the motivation. But that's what we had. This kind of shows how negative exponents work. And we could have, it might be easier or better for you if we started with x to the n over x to the n. We already discussed the subtraction rule. This is x to the n minus n, which is 0. And it's also x to the n plus negative n. Okay, so n, that's rewriting n to the negative n. Sorry, not x to the, not 0, x to the 0. And the rule that we had with where we add exponents led to multiplication, that shows that these are x to the n times x to the negative n. That might help clear it up a little bit. Let's see. So negative exponents. Take what the negative exponent is applied to. Its base. And move it to the other side of a fraction. By making the exponent positive. All right, let's take a look at some examples. Example, 10 to the negative 3. 10 to the third power would be easy to work with, but 10 to the negative third power isn't easy to work with. So what we do is we move it to the other side of the fraction and make the exponent positive. And then recall, exponents are, just tells you how many times to multiply the base together. The base here was 10, so 10 times 10 times 10 is 1,000. I do want to make a note of something. Let's do -5 to the negative 2 power, and then -5 to the negative 2 power like this. This one is saying -1 over 5 squared, which is -1 over 25. This one is saying 1 over -5 squared, and -5 squared is 1 over 25. Different signs. The negative in front for the coefficient part only applies to the 5 if it's in parentheses when you have exponents like that. Okay? That's a general rule of exponents. That general rule applies to normal exponents. -4 squared and -4 squared are different. This one is -16 versus this one is +16. So with negative signs, pay attention. With negative coefficients or negative signs in front of terms with exponents, the exponent only applies to the negative sign if it's in parentheses. Okay? So let's take a look at some more problems. Let's up our game a little bit with these negative exponents. If I've got like, let's go with 2/3 to the -2. We have the rule that we can distribute exponents on the outside to things on the inside. Because these are like really 2 to the first power and 3 to the first power. And when we distribute the exponent, we multiply it. And this is still 2 to the -2 over 3 to the -2. Now our negative exponents are going to make us flip which side they're on. This will be 3 squared, this will be 2 squared, and this ends up being 9 over 4. Okay? So this kind of combines a over b to the n and a to the -n equals 1 over a to the n combined make if we've got a over b to the -n, we can really just flip the fraction and make it positive. Notice that's what happened here. This is 3/2 squared. I can put the 2 back on the outside. So flip the fraction, make the exponent positive. I don't know that you need to memorize that rule in addition to the other ones. It kind of is a compilation of the other ones. We had, just as a quick reminder, where the a to the m times a to the n comes in. Look at x to the 4th times x cubed. The first x to the 4th is x times x times x times x. Then we've got x cubed, which is 3 x's multiplied together. And when we put them all together, we have x to the 7th, which is effectively showing that the exponents add. The same thing happened with subtraction. I believe we illustrated this before, but I will show it again. X to the m over x to the n is x to the m minus n. I used a before. Let's use like x to the 5th over x squared. Our example here. X times x times x times x times x on top, x times x on bottom. We can cancel terms that are multiplied together on top and bottom, leaving behind ones. This leaves us with x times x times x on top, and a 1 on bottom, which is just x cubed, and x cubed is 5 minus 2. That's just an example of where it comes from. It applies to any base. I didn't have to use any, I used x, it can use any base, and I didn't have to use 5 and 2. I could have used any numbers, but the principle applies. Note, these rules require the same base. Unless explicitly shown. Let me give you guys some examples to try out. How about you guys do 5 to the 6th power over 5 cubed? All right, let's assume you did. You could have multiplied the 5 out 6 times on top and the 5 out 3 times on bottom. You're going to get 5 to the 6 minus 3, which is 5 cubed. And this number is actually small enough that it's not too bad to write down. 5 cubed is 125. I'll give you another one to try. Let's do y to the 4th power over y to the negative 9th power. Okay, there's 2 ways you can look at this. I can rewrite it as moving the negative sign up top, or moving that negative exponent up top, and then applying the addition rule. Or we could apply the subtraction rule. Whatever's on top subtracts the exponent on bottom. but that turns into y to the 4 plus 9, which is again y to the 13. So sometimes these problems, especially with the exponents, there's multiple ways to get there. All right, let me give you one to try. The rules on this one are simplify. And we're going to start off with 35, a to the 8th power, b to the 11th power, divided by 25, a to the 12th power, b to the 5th power. Simplify and rewrite without fractions. That'll help clear up part of it. Okay. So this ends up being 35 over 25. Then we have a to the 8 minus 12, b to the 11 minus 5. 35 over 25, we should factor this and see what cancels. 35 is 7 times 5. 25 is 5 times 5. So 5s will cancel, and it'll leave us 7/5. And then we've got a minus 12 is -4, and 11 minus 5 is 6. So that was rewriting without fractions. In general, though, we prefer no negative exponents. So rather than leaving that as a to the -4, I'm going to rewrite that. We'll put that on bottom, 1 over a to the 4th, and then we've got b to the 6th. And the b to the 6th is really over 1. I can combine this to 7b to the 6th power over 5a to the 4th power. And that's the simplest form. Okay? Let me give you another one. Kick it up a notch. Let's do 5x cubed, and we're going to multiply that by 2 to the -1, x to the 4th, and we're going to raise that parentheses to the -3rd power. Go ahead and try to work that out real quick. All right, so we're going to, the 5x cubed, nothing's happening so far. We're going to move that -3 in by multiplying that -3 times each of the exponents. All right. And that gives us, then we got 5x cubed on the outside. -1 times -3 is +3, so that's 2 cubed. And 4 to the times -3 is -12. And 2 cubed, I can rewrite, that's 8. So we've got 5x cubed times 8x to the -12. I don't need the parentheses anymore because I've distributed the exponent. And now let's multiply coefficients. 5 times 8 is 40. And then I've got x to the 3 plus -12. It gives us 40x to the -9, or 40 over x to the 9th power. Okay. Let me give you another. I hope you're practicing these, pausing the videos and practicing them. Let's do 30 times r to the 4th power times s to the negative 9th power. And we'll divide all of that by 45 r to the negative 6th power s cubed. And simplify and rewrite without negative exponents. All right. Well, let's see. I can factor the 30. 30 is 6 times 5. And 6 is 2 times 3. So I've got 2 times 3 times 5. And the 45 on bottom is 9 times 5. And 9 is 3 times 3. So I've got 3 times 3 times 5. And what I'm going to do here is I'm going to move everything with a negative exponent to the other side. And things with a positive exponent, I'm going to leave where they're at. So the r to the 4th power and the s cubed stay on their respective sides of the fraction. I'll move r to the negative 6 up and make it positive. I'll move s to the negative 3 down and make it, or s to the negative 9 down and make it s to the 9. Now I can cancel out like terms that are on top and bottom. 3 and 3 cancel. 5 and 5 cancel. And remember, when they cancel, they leave behind a 1. And we are left with 2 on top. We will add the exponents. 4 plus 6 is 10. So r to the 10th power. On the bottom, we've got a 3 left. And we'll add the exponents there. 3 plus 9 is 12. We'll have 3s to the 12th power on bottom. Right. Here's another one for you. I'll start you off with 4b cubed. And we're going to raise that to the negative 2 power. And then we're going to have 4b to the negative 1. And I'll raise that to the negative 3 power. And then on bottom, I'm going to have in parentheses 4 to the negative 1 and b cubed. And all of that will be to the negative 4 power. Go ahead and try to work that out. All right, I'll assume you did. Let's distribute the negative exponents. And recall, anything without an exponent has an exponent of 1. So missing exponents equal 1. So that's 4 to the 1st power. And so is that one. So rewriting that by moving the exponents inside, I've got 4 to the negative 2 times 1, b to the negative 2 times 3, that's the first parentheses. Second parentheses is 4 to the negative 3 times 1, and then b to the negative 3 times negative 1. And on the bottom, I've got 4 to the negative 1 times negative 4, and b to the 3 times negative 4. Cleaning that up some, I've got 4 to the negative 2, b to the negative 6. And I really don't need that parentheses anymore, so I'm going to get rid of it. 4 to the negative 2, there we go. B to the negative 6. And then I've got 4 to the negative 3, b to the 3rd. And on the bottom, I've got 4 to the 4th power and b to the negative 12th power. And all right, so I can deal with the 4s. The 4 to the negative 2 times 4 to the negative 3 is -2 minus 3, and then, or maybe I should say plus -3. And then we subtract the exponent of the 4 on the bottom, so -4. And our b, we've got -6 plus 3 minus the exponent of the 1 on bottom, -12. This gives me 4 to the -9th power. And this gives me b to the 9th power. And when I rewrite that, I can put the negative, or 4 to the -9th on bottom. That's b to the 9th of 4 to the 9th power, which is probably how you need to leave it for math lab. I just did want to point out this is also b to the 4th power, or b over 4 to the 9th power, like that. This is one approach. There is another approach. Other approach. Move parentheses with negative exponents. What I mean by that is I could have put the 4b cubed on bottom and made the exponent 2. And I could have put the 4b to the -1 on bottom and made the exponent cubed. That one's squared, this one's cubed. And then I could have moved the bottom parentheses up to the top and made that -4 into a +4. And then gone through and done the same thing. So that's what I meant by moving parentheses with negative exponents. In all situations, you should end up with b to the 9th power over 4 to the 9th power if you did it correctly. All right? So let's kind of illustrate where radicals and exponents tie in, and I'm going to show you by using an example. So this is on connecting radicals with exponents. So the radical sign, or radical sign, is that. And if we have a number sitting out here on the shelf, n is the index. And unlike everything else in mathematics, if a number is missing in math, it's normally 1. If the index is missing, it's 2. And radical signs have to do with the roots. So let's just start with our example. I'm going to do the square root of 9. This is the square root of 9. When the index is 2, we call it square root. Square root. When it equals 3, we call it the cube root. And since the index was missing here, I could put it in and put a 2 there. Okay? And what it means is the index says how many times something needs to be multiplied together. I'm not saying that very well. Let me scratch that. Get rid of that. the square root of 9 is saying what times what equals 9. Okay? And we have two answers here. I could do 3 times 3 equals 9. And -3 times -3 equals 9. Okay? And the positive version, so what I have here is the square root of 9 is 3 or -3. We call that one the principal root. And what's going on here? Let me rewrite this and show the connection to exponents. So I've got square root of 9. And notice I put, a lot of people don't put this little tail down there at the end of the radical sign. I do. The tail at the end of the radical helps show where the radical ends. You'll avoid confusion if you use this approach. I can rewrite this as 3 squared, like that. And I know that has to equal 3. Okay? And I've got this 3 squared here, right here. What does the radical have to do? What must the radical do so that we end with 3 to the first power? Because that's really a 3 to the 1. And we know it's not subtracting exponents. If it was subtracting exponents, there would be a 3 on bottom. What it has to do is we have to multiply that 2 by 1/2. And to do that, that's effectively doing this. 2 times 1/2 will get us the 1. That works. That makes sense. And so this radical sign turns into parentheses 1/2. And if I put that little missing index in, the 2, maybe it helps show that the 2 is going to what's on bottom. Okay? Let's take a look at a cube root one and see what's going on there. And it might help it make it a little bit better. So cube root, 3 cube root of 8. This is really asking what times what times what equals 8. And we know that's got to be 2 times 2 times 2. The -1 doesn't work here. Notice that. -2 doesn't work on the odd roots, I'm going to say. The negative number in general doesn't work on odd roots. It doesn't give one of the answers. So the cube root, I can rewrite this 3 cube root of 8 as the cube root of 2 to the 3rd power. This equals 2. Cube root 8, I mean, you can do it in the calculator and see that. Shift cube root 8, 2. Okay. So I know this is equaling 2 to the 1st power. how we're getting there is the 2 cubed turns into, we got the 2 cubed in parentheses. The cube root sign turns into a 1/3. And that way, 3 times 1/3 equals 1, gives us that. Okay. So in general, this is where we start, where I was going with it earlier. The nth root of a, when I was doing the summary, is a to the 1/n. In this problem, my a was 2 cubed. In the last problem, I used 3 squared. But whatever's inside the radical gets raised to the 1/nth power, whatever the index is, okay? Other operations with roots. Other math tools for radicals. Or roots. Let's take a look at the square root of 8. Square root of 8. I can rewrite this as the square root of 4 times 2. 4 times 2 is on the inside. And nifty property of radicals, we can separate it. I can make this the square root of 4 times the square root of 2. And the square root of 4 is 2 times 2. Or 4 is 2 times 2, so the square root of 4 is 2. And then I still have that square root of 2 there. Okay? So that's the answer for square root of 8. If I look at this in exponents, check out what happens in exponents. The exponent version. Square root of 8 is, I'm going to rewrite that 8. We just showed that 8 was 2 cubed. And if I use the rules we had, I can put this as, I've got 2 cubed times 1/2. The radical goes out as a fractional exponent. And we multiply them, that's 2 to the 3/2. And 3/2 is really 1.5, right? And 2 to the 1 1/2 is 2 to the 1. I'm just rewriting the 1 1/2 as 1 plus 1/2. And that might help make it easier to see the property that that can be split up into multiplying 2 to the first times 2 to the half. 2 to the first power is just 2. And when we have something with a 1 over a number as the exponent, that becomes the square root, or the 1 over 2 as the exponent becomes the square root. It helps to put a little ledge there. It helps to emphasize the ledge. Make it clear that that 2 up there is the index. Okay? But let's take a look at that 2 to the 3/2. What did we do with that 2 to the 3/2? And how did it, where did it come from over here? It was stuff inside there. So 2 to the 3/2, this is like if I had a variable to the m over n. Now, with the 3/2, I showed the 3 on the inside and the 1/2 on the outside. I can definitely show that as x to the m over 1 to the n. And these are multiplied. So like I could actually put the 1 over n on the inside and put the m on the outside. Because m over n equals m times 1 over n and commutative rule. Commutative property. And the 3, we had 2 to the 3/2. The 3, the m on top was inside the radical. And the denominator of the exponent was the index. Okay. Showing that is this one right here. And what I showed here, we can actually put the m on the outsides because these are multiplied. This is the same thing as the nth root of x raised to the mth power. That's rewriting that. I didn't bring my little tail down. There we go. Okay. This is radical notation versus exponential notation. Hopefully you're comfortable with both by the time you're done with this class. We will do more stuff with this in later sections. This is a review of some basic algebra or basic properties of numbers that apply. This is not algebra. I'm not doing algebra yet. This is basic arithmetic, rules of exponents and radicals. I may be using letters to indicate that it applies to any number, but these are not algebraic rules. So let's look at some examples and let's simplify some examples. Example, and we're going to simplify. Let's simplify 81 to the 3/4 power. All right. So I think it might help to let's look at what 81 is. 81. Oops, I bumped my document camera. 81 is 9 times 9, and 9 is 3 times 3, and 3s are primes, and I've got 4 3s, so 81 is 3 to the 4th power. And I still have my 3/4 on the outside. So that's all I'm doing right there, is I'm rewriting 81 as 3 to the 4th power. And now the properties here is this becomes the rules of exponents as I multiply them. I multiply 4 times 3/4. To do that, I'm going to make that 4 a 4 over 1. Anytime we got a whole number, I can make it over 1. I multiply the exponents. Remember, things on top and bottom cancel. And I'm left with 3 cubed, which is 3 times 3 times 3 is 27. Okay. So that's what that ends up being. I do want to point out sometimes this. A lot of people like to work with this in radical form, and I really don't. The 81 and 3 to the 3/4. I can rewrite this as the 4th root of 81 cubed, but 81 cubed is ginormous. 81, oops, times 81 times 81. 531,441, and I don't know the fourth root of that. I don't think this is helpful. I could put the 1/4 on the inside. I could say this is the fourth root of 81 and put the cube on the outside. And this is usable, but I think working with the fractions was easier. We're going from here. What I would do here is I would try to write the 81 as a prime thing to a power. This is the fourth root of 3 to the 4th cubed. Which is 3 cubed. The fourth root and the 4 cancel out. Let's see. Is that the only answer? Nope. I could rewrite 81 is also -3 to the 4th power. So this could have been -3 cubed, which is -27. We tend to go with the principal root or the positive root unless we're dealing with, I'll make a note of that on the next one. We tend to use the principal or positive root. Unless we are solving a algebraic equation. Where we will use both roots. And we'll get to that. So let me give you another example. We've got 25 to the 3/2. I can rewrite that as 5 squared to the 3/2. And treating these as fractions, 2 is 2/1, and the 3/2 goes on the outside. The 2's cancel. This ends up being 5 cubed, which is 125. And if I show how manipulating it around other ways, writing this as the square root of 25 cubed is helpful. A lot of people know what the square root of 25 is. That ends up being 5 cubed. The other way of writing this is the square root of 25 cubed, and that's not helpful. You have to cube 25 and I will show you what I would do to go from that point. If you have something like that, I would do this. I would do 25. I would rewrite the 25 as 5 squared cubed, like that. And what this means is I've got, well, I multiply exponents. I got 5 to the 6th power. What I'm going to do when you have an exponent that's bigger than the index is a 2. When exponent inside radical is bigger than index, then the index of the radical, split the exponent up into I'm going to say index size pieces. And I'll show what I mean here, and then I'll give you another example real quick. So the index is 2. I'm going to split 6 up into terms of 2. So I've got a 5 squared, and I've got a 5 squared, and I've got a 5 squared. 2 plus 2 plus 2 is 6. That works. That's split into index size pieces. And each one of these I can write as 5 squared like that, 5 squared like that, 5 squared like that, which equals 5 times 5 times 5, and we get our 125. Let me make it this splitting up into exponent size pieces a little bit clearer. Let's say I've got the cube root of x to the 8th power. So this is my example of what I meant by the last thing. What I'm going to do is I'm going to take that 8 and I'm going to just keep subtracting 3 from it and writing them down. So if I do 1x cubed, I've got an x to the 5th. And I do another one, I've got x squared left. These ones can come out completely. And they cancel index. So I pull those out. I've got x times the cube root, and x squared, there's nothing I can do with. So I would write this as x squared cube root of x. And maybe I should do that on another page real quick, because I didn't do a very good justice in illustrating a good point. Cube root of x to the 8th is x times the cube root of x squared. I'm bypassing that middle step right there that I did. This is x squared times cube root of x squared. And when you put them together, you really, this is why you want to make sure that that 3 right there is clearly on a ledge. Make sure the 3 or index and this is why. If I wrote that as I've got x squared cube root of x squared. The ledge is funny, and if I had lined up the 2 and the 3 a little bit better like that, let's do it like that. Is this x to the 23rd times the square root of x squared, or x squared times the cube root of x squared? So one of them makes the index pretty clear. These are different answers though. So make sure you put that index clearly on something. Another example. If we've got -4 to the 5 halves, I do not have the negative in parentheses, so it's on the outside. That's what's really going on there. And I can move that. I think it's easier to move the 2 in and make the square root. Which is negative 2 to the 5th power, and that's negative 32. Or I could put the 5 on the inside. This is negative 4 to the 5th power to the 1/2, or the square root of 4 to the 5th. Less helpful. But still usable. Doing what I said before, I could rewrite that 4 to the 5th power is 4 squared times 4 squared times 4. And when the index match or the exponent matches the index, note the invisible 2. Invisible index. When the index matches the exponent, you can pull it out. 4 times 4 times, that one doesn't match, so I got to leave it as square root of 4. And 4 times 4 is 16, square root of 4 is 2. That's 32, but I still have a negative sign out front. So it's workable, but I do want to point out something to be aware of. Be careful with negatives. Inside radicals. Let's see. Let me pick a good one that works. Well, we got negative 100 to the 3/2. This is effectively the square root of negative 100 cubed. And the square root of negative 100 is not a real number. It's actually imaginative or imaginary number. This ends up becoming a complex number. And the reason why, there is no real number that has an even root of a negative number. No real number has an even root of a negative number. And I can be a little bit more clear. I can illustrate that a little better. Square root of negative 100 corresponds with question times question equals negative 100. And the question mark is a question mark can't be a real number. Because positive times a positive is positive, and a negative times a negative is positive as well. There is nothing that where we have the same sign. This is really saying something squared equals negative 100. Not possible in the real numbers. All right. Just for a second. All right. let's do a little bit more. I need a little restroom break, and you don't need me to do that on the video, right? You should be pausing this video to take breaks when you need. The next two examples are going to lead to an idea. So let's look at 216 to the negative 2/3. Now we've got negative exponents and fractions. Recall the negative exponent says I can do this. I can put the 216 on bottom and write that as 2 cubed. And now I can split that up. That's the cube root of 216, and we're going to square it. Square it. And that is 6 squared, which is 1 over 36. Versus our other example, let's do negative 64. Let's put the negative in there, and we've got that. This is, I can make this the cube root of negative 64 squared. And 64, just factor real quick. 8 times 8, which is 222 and 222. So I've got the cube root of negative 2 to the 6th power squared. And we'll do what I did last time. This becomes, when I've got something this, I'm going to break the 6 up into 3 size pieces. Cube root of negative 2 cubed. And then I've got another negative 2 cubed. Still got the square on the outside. The root and the index and the exponent cancel out. This is negative 2 times negative 2. I'm doing this bad. That is not correct. The negative is on the outside. Negative's on the outside there. That's what's wrong. So I'm going to rewrite that as the cube root. 2 cubed times 2 cubed is, I could do that as the same thing as 4 cubed, right? And here the negative can go inside. Is negative 64, can I do negative 4 times negative 4 times negative 4? Negative 4 times negative 4 is positive 16 times negative 4 is negative 64, yeah. So now I can move the negative inside. Cube root of negative 4 cubed like that, that works, that makes sense. The way I had it before, I kind of screwed that up a little bit. And this becomes negative 4, the cube and the cube root cancel. I still got the square. This is positive 16. So maybe skip that step right there. Don't do that. That's a little distracting. That's a little distracting as well. We're going to take those and break it up into 4 times 4 times 4. That's what we're doing. My general rule that I wanted to talk about here, fractional exponents. Like m over n. If n is odd, like having the cube root or fifth root, something like that. This will always work. Let's say this was x to the m over n, and this is x to the m, x to the m, where I just assigned n equals 3 or n equals 5 there. This will always work. If n is even, for example, the square root of x to the m, fourth root of x to the m, sixth root of x to the m, etc. We need the inside to be positive for a real solution. Okay. And here's a little table for you. Well, n to the first power is just the same number. N squared, hopefully you're familiar with. $36, $49, $64, $81. These are from the multiplication table. The one you may not have memorized, n cubed, 64, 125. This is 216, 343, 512, and that's 729. Memorizing n cubed up to maybe n equals 5 is handy or easy. Is easy. Hopefully, just try to memorize these, or if you see them, maybe it'll trigger a memory that maybe this is something to an exponent. Okay. So let's do some more stuff with exponents, radicals. Let's do our first example. 18 to the 1/2 times 18 to the 7/2 over 18 cubed. We'll deal with this stuff on top. We have the same base, which means we can add the exponents. And adding the exponents gives me 8 over 2. And 8 over 2 is 4, and I can subtract the exponent on the bottom. This is just 18. Okay. Let's kick it up a notch. We'll have different bases here. 100 to the 3/2 times 16 to the -3/4. So let's take a look what happens. I'm going to rewrite that negative exponent as a positive one by moving that base to the bottom. And this is the square root of 100 cubed. And this is the fourth root of 16 cubed. Okay? Which is square root of 10 squared cubed over fourth root. If we rewrite 16, it's 2 to the fourth cubed. And now it might be easier to see, oh, if we put the invisible index in of a 2, this ends up being 10 cubed over 2 cubed. Which is, that's 1,000 over 8. That's a little challenging. I would do a calculator for that. Notice, shortcut, no calculator. Since they're both cubed, I can pull that cube out and make this 10 over 2 cubed. But that's just 5. 5 cubed is 125. And if I did 1,000 divided by 8, I should get that. So I did it without using a calculator. Sometimes doing that makes it the problem easier. Okay. Let's kick it up a notch. Now we'll throw some variables in. X to the 3/4, and we'll multiply that by 5x to the 2/5. Here we're multiplying, we multiply the coefficients separately. And then I've got x to the 3/4 times x to the 2/5. And well, 4 times 5 is 20. And I've got a common base, which means I can add exponents. 3/4 plus 2/5. Now, you can't add fractions without a common denominator. Don't forget that. So I'll just take the denominator of 1 and multiply it by the other. 5, I'll multiply this by 5 over 5, and I'll multiply this one by 4 over 4. And if I do that, I now have 15 over 20 plus 8 over 20. Because when you multiply numerators and denominators separately. And now I can add them. 20x to the 15 plus 8 over 20 is 20x to the 23 over 20. Depending on if they accept that as where you can leave it, that's valid. This is also 20x to the 1 and 3/20 if we turn that fraction into a mixed number. And that would make this 20x and then the 20th root of x cubed. I think that's a good stopping point, though. Okay. I'll give you one to try. Y to the 3/7 We're going to multiply that by y to the 4/7 minus 5y to the 11/7. Now, even though these exponents have the same denominator, we're not multiplying these things, so we cannot combine these. So can't combine these two. Let's distribute. So I've got y to the 3/7 times y to the 4/7. And I got minus, and I can do y to the 3/7 times 5y to the 11/7. Now we can combine the y's the way they are because they have a common denominator and it's through multiplication. This is y to the 3 plus 4/7 minus 5y to the 3 plus 11/7. And that's 3 plus 4 is 7. And 3 plus 11 is 14. And those are actually perfectly divisible. Let's just do it. 7 divided by 7 is 1. And when it's an exponent, we don't write it. And then 14 divided by 7 is 2. So that whole thing simplified to that. Now, to illustrate the next property, I'm going to illustrate the reasoning of the next property. I'm going to go back. I'm going to re-show greatest common factor. Let's say I started off with 12x squared minus 8x cubed. Twelve is 4 times 3 is 2 times 2 times 3. 8 is 2 times 2 times 2. And then I've got x times x times x and x times x. The GCF is the full columns. 2 times 2 is 4, and x times x is x squared, 4x squared. What did that leave behind? 3x. Then I got my minus sign and a 2. Note this is the same thing as doing 4x squared and taking the original things that we had and dividing them by the 4x squared. Same thing. In fact, that's how we do the greatest common factor. That's why it can come out. What I want you to notice is the exponent that came out was the lowest exponent or least exponent. Okay? This applies to negative exponents. All right? That principle applies negative exponents as well. All right. For example, 28y to the negative 5th plus 21y to the negative 2. Well, if I look at the 28 and 21, that line there, 21. This is 7 times 4, which is 2 times 2. This is 7 times 3. The GCF is a 7 for the numbers. So I'm going to pull out a 7. And the lowest exponent is negative 5. You will find this might be a lot easier to do this like this, rather than trying to jump to a shortcut, actually showing it being divided out. Okay? Show it being divided out. And the reason why, well, 28 divided by 7 is 4. And now I can do the negative dividing exponent, or dividing bases, common bases with different exponents. This is y to the negative 5 minus negative 5. And then 21 divided by 7 is 3. And I've got y to the negative 2 minus negative 5. Ultimately, I end up with 7y to the negative 5th, 4y to the 0. Negative 5 plus 5 is 0. And negative 2 minus negative 5 is plus 5. Negative 2 plus 5 is 3. So I've got 7y to the negative 5th. Y to the 0 is 4, or 1. So 4 plus 3y cubed. Okay? That's how you take out and factor out a negative exponent like that. Note that doing this and having the negative 2 and ending it with a 3, it to me isn't that intuitive. Factoring out the y to the negative 5th out of a y to the negative 2nd isn't that intuitive to me. And so rewriting it like this and showing what's happened shows me getting the y cubed, and I can see that, and that's an operation I know. And I've been working with math for a while, and that's still not intuitive to me, that factoring out a y to the negative 5 out of a y to the negative 2 is going to end up with y cubed. So even with a lot of experience with something like that, it's not intuitive. Okay? I did write this out because I wouldn't recognize that's y cubed. If you do, more power to you. Much respect. I don't. And so don't be ashamed or embarrassed if you don't either. Write out what's going on. This is a little scary factoring that out, right? Factoring out a y to the negative 5 out of that's scary. That's intimidating. But if we show it being divided and we do the whole x to the m over x to the n equals x to the m minus n, apply that, is less scary. Makes this a lot less scary. Okay? Because that's an easy operation. Subtraction is easy. Doesn't just apply to negative exponents, applies to fractional exponents as well. So let's take a look at one of those. let's do 18n to the 7/3 minus 24n to the 1/3. Between the 18 and the 24, 18 is 6 times 3, and 6 is 2 times 3. So I got 2 times 3 times 3. 24 is 6 times 4, so I've got 6 is 2 times 3 times 4 is 2 times 2. The GCF is 6. So I can pull out a 6. Lowest fraction is 1/3. So I'll pull out an n to the 1/3. And do the same thing I did before. I'm not just going to try to Jedi mind trick it and figure out what it is. Try to think that I'm clever. I'm going to actually show the operation, because that's a lot easier. I mean, it can be good to practice doing some math. Definitely is good to practice doing math in your head and then seeing when you write it down on paper, working it out, seeing if it works. I do that a lot. That's how I've gotten pretty good at memorizing all the cube numbers. I can square 2-digit numbers pretty easily doing this with practice. But some things I haven't practiced very much. I haven't practiced dividing out or factoring out negative exponents or fractional exponents enough that I can do it in my head. So I won't. I've got 6n to the 1/3 on the outside. 18 divided by 6 is 3. And now I can subtract those exponents right there. 24 divided by 6 is 4, and I can subtract the exponents here. Six n to the 1/3 on the outside. 7/3 minus 1/3 is 6/3, which is 2. So I get 3n squared. 1/3 minus 1/3 is 0. So I've got minus 4n to the 0. N to the 0 is 1, so I've just got minus 4. Another way to recognize that this n goes away, or I got n to the 1/3 on top and bottom, I can cancel them out. Okay? Now, earlier I was using, if we had the nth root of a to the n, we were showing it equals a, and this is only true sometimes. It's the negative numbers that screw things up. I was telling you about that. Only true. Wow, I totally just jacked the word sometimes by speaking while writing. Only true sometimes. There we go. For example, if we've got x squared, if x is -5, then this turns into square root of -5 squared is the square root of 25, and we tend to say that equals 5 by going with principal root. So what we want to do is when we have an even root, when n is even, use this rule. Notice if I followed the property up there, this should equal x. Is that true if x equals -5? No, it ended up being +5. So what we're going to say is we're going to do this. The nth root of x to the n, if n is even, is the absolute value of x. If x is positive or negative, we're going to use the positive one, okay? And what that really means is this equals A if n is odd. Or X if n is odd. And equals absolute value of X if n is even. If I get rid of the n is even property, I can make that generalization. Okay? So let me let that stew for a second. I'll give some examples. So let's do the square root of z to the 6th power. I could rewrite this as the square root of z cubed squared. And with the variables, I want the 2 on the index and the 2 and the exponent cancel. We're going to leave behind the absolute value of z cubed. Okay? Note, this is funny. Square root of z to the 4th. I could do the same thing. Z squared squared. And I could write that as the absolute value of z squared. But when I square something, doesn't it make it positive anyways? Squared things are positive anyways. Don't need the absolute value. This is just z squared. Don't need it anymore. So even exponent inside there makes the absolute value signs irrelevant. Value bars irrelevant. And well, if you want to try out an odd exponent, when we do cube root of w to the 9th, this is w to the 9 over 3, which is w cubed. The other way of writing this is cube root of w cubed cubed. And then we apply the rule we had, the cube root and the cube cancel out, and we're left w cubed. Okay. Let me give you guys one to try. You try. We're going to do the square root of 81r to the 8th, s to the 10th. Guess I didn't need that extra absolute right tail right there. Write this solution. Pause it if you need a while. This is the square root of 9 squared, r to the 4th squared, s to the 5th squared. And I really have, I put the little index on a counter out there, that's a 2. So the curtains match the drapes, the index matches the exponent. This becomes the absolute value of 9, r to the 4th, s to the 5th. But 9's already positive. It doesn't need the absolute value. That's the absolute value bars. And r to the 4th is going to be positive anyways because it's an even exponent. So the r to the 4th can come out. The 5, though, we need to make sure if it starts off odd, it would be odd. Or if it started off negative, it would be negative after the 5th power. So we're going to write it as that. Something else, I want you to be careful if you see something like this. Don't just cancel out the square root and the square. This is going to be the absolute value of 3x minus 4. Because we don't know if 3x minus 4 is negative or less than 0. Okay? Now, I'm going to do the next one illustrating something. Let's take a look at the cube root of 8 times the cube root of 27. That's the cube root of 2 cubed times the cube root of 3 cubed, which ends up being 2 times 3, which is 6. Okay? And 6, also I want to say this. The cube root of 6 cubed is also 6, right? But I could write that as the cube root of 2 cubed, or 2 times 3 cubed, which equals the cube root of 2 cubed, 3 cubed. Which is the cube root of 8 times 27. These both led to a 6. Notice what happened. If indexes match, or indexes, plural of index is indices. If we match the index, we can multiply what's inside. And if MATLAB throws it at you, it's called the Radicand. It's some math jargon. Okay. General rule. Nth root of square root of a, or nth root of a times the nth root of b equals the nth root of a times b. Here I used 8 and 27 as examples, and n is 3, but this property holds. This also holds for division. Nth root of a over nth root of b equals the nth root of a over b. And for the same reasons, it worked as exponents. We can rewrite the radicals as exponents, and these properties of exponents happen. These were true. A final one, and this one does not come up often. They might throw you a problem in MATLAB. The mth root of the nth root of x equals the m times nth root of x. This might be a little bit easier seeing it as exponents. The nth root of x is x to the 1 over n. And then the mth root is like that. So I have x to the 1 over n to the 1m, which is 1 over n times m. And that gets us back to there. Okay, let's apply that a little bit. This allows us to work with roots of different numbers. This is really, really handy. This allows us to work with roots of different numbers. Numbers or values. Square root of 5 times the square root of 45. Well, I can put those together. 5 times 45 is 225, and that's 15. But what if I don't have the square root of 225 memorized and I don't have a calculator? This is the square root of 5 times the square root of 9 times 5, which is square root of 5 times square root of 9 times square root of 5. I can split that radical up. That's what I just said. We can have two different radicals and put them together. And now, well, this is 3. And this is square root of 5 squared, which is 5. So I get 3 times 5, 15. Or you could look at this as putting the 5s together, square root of 25 times the square root of 9. And then you get 5 times 3 is 15. So many ways to work with it. So if we have like the 5th root of x cubed, and we multiply it by the 5th root of x to the 5th, or x squared, well, that means I can put those together. And we know that means we can add the 3 and the 2. And I've got the 5th root of x to the 5, and that's x. Okay. This can make doing some operations easy. Let's see, what do I want to pick to do? Let's look at square root of 25 over 144. 25 over 144 is an ugly number. It's a decimal. But what if I make this the square root of 25 over the square root of 144? Square root of 25 is 5, and the square root of 144 is 12. It's called a gross. And 5/12 isn't too bad. That's just a small fraction. Another example. Well, let's do the square root of 11 over 169. Let's try to clean this up. I can split that up into the square root of 11 over the square root of 169. And 169 is a perfect square. It's 13 squared. So I can end up putting a 13 on bottom. 11 is not a perfect square, so I'm going to leave it as a radical. Okay? So how do I know when a radical is simplified? What's the rules for that? Let's talk about the rules of when a radical is simplified. And I'm going to use words, so I'm really going to illustrate this. I've got the index on the outside. That's the radical symbol. What's inside is called the radicand. That's what goes on the inside. So radicals are simplified when A, the radicand has no factor with an exponent larger than the index. B, no fractions inside a radical. Really boils down to no fractions. This makes it also no fractions or no radicals on bottom. That's like, we'll call that C. D, exponents and index have no common factors. What I mean by this, make this a little clearer. Like if I had the 6th root of x squared, they have a common factor. 6 and 2 both have 2 as a multiplier. This is equal to the cube root of x. That kind of idea. And all operations have been performed. So let's look at some examples. Pause this if you need this up longer. This video is a little longer than I like it. I've been being a windbag. I apologize. I hope putting the summary of the properties on the front was helpful. So let's do an example. Several examples. Let's look at the square root of 27. This is the square root of 3 cubed. And what was the first rule? The exponent can't be larger than the index. The index here is a 2. The exponent is larger than the index, so this is not simplified. So what I need to do is I can break that 3 and the exponent up into 2 plus 1. And this becomes 3 squared times 3, which equals square root of 3 squared times square root of 3. And the first one simplifies to 3, but the second one stays the same. It is common notation to put the radical last. Root 3 or x root 3 is not confusing. I know that the number in front is multiplied by it. But root 3 like that, or root 3x, sloppily written, or the way typewriters do it, looks like square root 3 without a tail there, 3 like that, or root 3x. Is this inside the radical? So that's confusing. It can be confusing. This was just one way of doing this approach. I do want to point out also, or we could do square root of 27 is the square root of 3 cubed, or 3 cubed to the 1/2. And we multiply exponents there, 3 to the 1/2. But 3/2 is the same thing as 1/2. And I can write that 1/2 as 1 plus 1/2, which is 3 to the first power times 3 to the 1/2, which equals 3 root 3. And I only wrote all that out to show what I was doing. With practice, going from 3 to the 1 1/2 to 3 square root of 3 gets easy. With practice, everything gets easy with practice. Well, easier. If you do something enough, it can get easy. At least easier. All right, let's look at another example. Let's do, I'm going to have -8 times the cube root of 16. Well, that's -8. And then, well, 16 is 2 to the 4th power. So I'm going to write that 4. I want to break it up into index size pieces. 3 plus 1. And pull out, separate those two, cube root of 2 cubed times cube root of 2. And the cube root of 2 cubed is 2. And we still have cube root of 2 there. So this is -16 cube root of 2. again, with practice, going from here to here gets easy with practice. Well, maybe to here. Getting the 2 out, pulling out the 2. Let's say that. Gets easy with practice. Other examples, 170 square root of 175. You should factor it. 175, that's 7 times 25, which is 7 times 5 times 5. So I've got, that's 7 times 25. And I can split it up. Square root of 7 times square root of 25. But we know square root of 25 is 5. So I've got square root of 7 times 5, and we'll put the 5 in front for common notation. 5 root 7. That's simplified. Let's make it, let's give you a challenging one. Go big or go home, right? Go big or go home. And you're like, I want to go home. I'm done with this, right? No, you're not done with this. Go big or go home. The harder homework is, the easier tests feel. True story. If I give you the most miserable homework ever, then any test has got to be the same level of difficult or easier. It can only go downhill, right? Go big or go home on the homework. Cube root, let's do this. 128, x to the 6th power, y to the 8th power, z to the 10th power. I want you to simplify that. So I'm going to assume you pause. I'm going to deal with the 128 first. What is 128? 128 is, well, it's 64 times 2. 64 is 8 times 8. And each 8 is 3 2s. So I've got how many 2s? 7. This is 2 to the 7th power. So this is the cube root of 2 to the 7th, x to the 6th power, y to the 8th power, z to the 10th power. And I'm going to break up those exponents so that they're multiples of 3. Let's say this is 2 to the 6th times 2 to the 1st. X to the 6th still works. I'll do y to the 6th times y squared. And z to the 9th times z to the 1st. The ones that are multiples, the exponent is a multiple of 3, or the index can come out. So like you're looking for 3, 6, 9, 12, 15 when the n equals 3, the index. That's where I chose 6s and 9s. So if I pull them out, I can really write that as 6 over 3, and then y is 6 over 3, z is 9 over 3. What's left over is I got the cube root. I'm going to make sure that 3 looks like it's on a ledge. And I've got a 2 to the 1st power still inside, a y squared still inside, and a z to the 1st power still inside. And when I clean that up, 6 divided by 3 is 2. 9 divided by 3 is 3. So I've got 2 squared. 2 squared is 4. Y squared z cubed. And then the cube root of 2y squared z. We're going to do some more stuff. We're going to do some more working with some radicals. I do want to show you how to estimate a radical without a calculator. Like, let's say I want the square root of 7. What is the square root of 7? What is that? Well, the square root of 7 is going to be, well, it's going to be higher than the square root of 4, and it should be less than the square root of 9, which means the square root of 4 is 2. I've got 2 is less than the square root of 7, less than the square root of 3 is 9. 7 is closer to the 9, so it's probably above half. 7 is closer to 9 than 4. So probably above 2.5. Or the halfway mark, maybe 2.6. So I'm going to estimate square root of 7 is about 2.6. And we use wavy lines, not equal signs, when we're approximating. What is square root of 7? $2.645. 2.6457 would round up to 5 to 6. So that's not a bad estimate. And I just eyeballed that. I just winged it. Okay. A little bit more. Operations with radicals. I said you can't have any operations left, so getting rid of the operations with radicals. Let's just start with a big one. Let's do like square root 11 plus square root of 17. Well, first off, I'm going to do one that's actually kind of easy. And actually leads to a rule. So we distribute. I got square root of 11 times square root of 11. And then square root of 11 times negative square root of 17. So minus square root of 11 times square root of 17. And then I do FOIL inner operations plus square root of 17 times the square root of 11. And then I got minus square root of 17 times the square root of 17. So this is, well, I've got square root of 11 and I've got it twice. That's square root of 11 squared. 11 times 17, I can put them together in one radical. That's 187. And I have plus 187. And then I've got minus, well, that 17 square root is multiplied twice. So I've got that. These cancel. Plus and minus the same value cancel or equal 0. So I've got square root of 11 squared is 11. And then minus square root of 17 squared is 17. 11 minus 17 is negative 6. Notice no radicals left. If you have the square root of a minus the square root of b, and you multiply by the square root of a plus the square root of b, you just end up with a minus b. These two are called conjugates of each other. Conjugates of each other. Notice the sign between them is the only difference. What about when they're not something like simple like that, where they are equal to each other? What happens when we have different numbers? Let's take a look at that. So let's do like 5 plus square root of 32 times 3 minus square root of 2. We need to distribute. So I've got 5 times 3. And then 5 times negative square root of 2 is minus 5 root 2. And then I've got plus square root of 32 times 3 is 3 times square root of 32. And then I've got square root of 32 times negative 2, or minus square root of 32 times 2, square root of 2. And what can we do? Well, 5 times 3 is 15. That simplifies. 5 root 2, it's prime inside. Nothing can go on there. 32, if I factor it, I could write that as 16 times 2, right? And here I can multiply the 32 times the 2 together, and I have minus the square root of 64. Well, the 15 and negative 5 root 2 don't change. But this becomes, the square root of 16 is 4. This becomes plus 3 times 4 root 2. And square root of 64 is 8. So I've got 15 minus 8 is positive 7. And 3 times 4 is 12. And what do we do when we add? When the radicand is the same? We add coefficients. So this is 7, and then so here, negative 5 root 2 plus 12 root 2, we add them is negative 5 plus 12 root 2. And if we do that, we've got 7 root 2. Okay. And that requires the radicand to be the same. Note the radicand, or what's inside, must match. So 6 root 3 plus 8 root 3 matches. Six root 5 and 8 root 3 does not combine. If it helps you see it, replace radical with the variable. like x. I'm going to let x equal square root of 3. This is like 6x plus 8x now. Well, that's 14x. And now I'll put the radical back in. And now put radical back in. Okay. What about when we got a radical on the bottom? What do we do when a radical's in the bottom? Denominator of a fraction. Like 2 over the square root of 7. What you want to do, multiply top and bottom by that radical. And I'm going to say, or conjugate if there is a plus or minus, if there is addition or subtraction. So that means here, what I'm going to do is I'm going to multiply the top and the bottom by square root of 7. This becomes 2 times the square root of 7 over square root of 7 times square root of 7 is 49. And this becomes 2 root 7 over 7. Sometimes maybe multiplying top and bottom by that radical is not the best answer. Let me rephrase that. I'm going to get rid of the by that radical. Multiply top and bottom such that the exponent is 1 on bottom. And the reason why, well, this one, it works just fine. If I rewrite square root of 7 as 7 to the 1/2, well, 1/2 plus 1/2 would give me 1. And to do that, I need to multiply the top by that. A little bit more complicated, though, if it's not a 1/2. Five over the cube root of 4. This is 5 over 4 to the 1/3. What do I got to multiply by so that I end up with 4 to the first on bottom? And it's got to go through addition. I need to use a 2/3. So I've got 5 and then the cube root of 4 squared, which is 5 cube root of 16 over 4. We can make that a little bit uglier. put a radical on top. Let's do the cube root of 4/9. This is the cube root of 4 over the cube root of 9, which is the cube root of 4 over 9 is 3 squared. So this is 3 squared and then the 1/3 like that. Or cube root of 4 over 3 to the 2/3. What I got. So if I want to end up with just the 3 to the first power on bottom, I got to multiply by 3 to the 1/3 on top and bottom. So I've got cube root of 4 times the cube root of 3 on top. And now I've got 3 on the bottom. And the indices match, so I can put these together. This is cube root of 4 times 3 is 12. And the bottom is 3. Or you could write this as 1/3 times the cube root of 12. All right. Let's see, what else can I give you to bake your noodle some? Well, it gets more complicated. Let's up our game. Cube root of, let's do x to the 5th y divided by cube root of x squared y to the 5th. Well, since they're both the cube root, I can put that on the outside and put the radicands on the inside. And using the subtraction rule, I got x to the 5 minus 2, y to the 1 minus 5. Cube root of x cubed, y to the negative 4. Let's put that back on bottom. And I can now separate that back up, x cubed like that, with cube root on the outside like that, over cube root of y to the 4th, and I'm going to break that up into index size bytes, y cubed times y, so that the index cancels the exponent. I get x out over here, and I get, oops, that should be a y right there. I get y cube root of y on bottom. Let's see. Make another hard problem. We're almost done. Almost done. Couple more problems. Woo, long section, huh? We've been doing this 2.5 hours. Feels like it. Let's do the 4th root of 6 over x to the 8th minus the 4th root of 3 over x to the 16th. You should definitely break these up. 4 root 6, or the 4th root of 6 over the 4th root of x to the 8th minus the 4th root, 4th root of 3 over the 4th root of x to the 16th and while the numerators are stuck the way they are, x to the 8th and the 4, well, that would be the absolute value of x squared, right? But we don't need the absolute values because it's squared, so I can get rid of that. Don't need the absolute values. And then I got the 4th root of 3 over 16 divided by 4 is 4. So I've got the absolute value of x to the 4th. And again, 4 is an even power, so I don't need the absolute values, not needed. Not needed for even exponents. Exponents inside. So what do I have there? I've got 4th root of 6 over x squared minus 4th root of 3 over x to the 4th. That's not really all that cleaned up. You should probably get a common denominator. If I multiply this one by x squared over x squared, then I got x to the 4th on both. And then we can combine them. And make sure that ledge is clear. That's probably your cleanest answer. Doesn't have to be pretty to be right. Now, the only other one that we really have that we want to work with is, well, what about when there's adding or subtracting in the denominator? What about addition, subtraction of radicands in the denominator? Of radicals in the denominator. I'm going to give you an example, show you how to do it, and then I want you to do one, and then we'll call it a day, all right? So what I'm going to do, let's start with 2 over, let's go 3 plus square root of 5. When you have addition or subtraction with radicals in the bottom, multiply by the conjugate of the bottom. Conjugate of the bottom is we just changed the sign. So 3 minus square root of 5. And you probably should put these in parentheses because you need to distribute. So I've got 2 times 3 minus square root of 5 on top. And 3 plus square root of 5, 3 minus square root of 5 on bottom. Distributing, 2 times 3 is 6. And 2 times negative square root of 5 is negative 2 square root of 5. That's the numerator. The denominator, if I distribute, 3 times 3 is 9. Then I've got negative 3 root 5 FOIL. Inside is next plus 3 root 5. And then minus square root of 5 squared, or minus square root of 25. Those cancel, and square root of 5 is 5. I get 6 minus 2 root 5 over 4. That actually simplifies some, doesn't it? This is 2 times 3 minus root 5, what I started with, over 2 times 2. And if I cancel that, I get 3 minus root 5 over 2. And MATLAB probably wants you to break this up. 3 halves minus root 5 over 2, or 3 halves minus 1/2 root 5. The shortcut to the conjugate. Notice it ended up being just a whole number, right? I had 3 plus square root of 5 and 3 minus square root of 5. What if I said this was a plus b and a minus b? We got a formula for that, don't we? That's the difference of squares, a squared minus b squared. Well, a equaled 3 and b equaled square root of 5. So putting those in, I got 3 squared minus square root of 5 squared. 9 minus 5 equals 4. And then you don't have to multiply it all out. All right, one example for you to do, then I'll help you through it, but I want you to try to do it on your own. This is going to combine all sorts of crap. All sorts of crap. You try. 4 plus the square root of 3 over 5 minus the square root of 3. Simplify. All right, I'm going to assume you paused it to do it. We multiply by the conjugate of the bottom on numerator and denominator. And I'm going to put these in parentheses. This is 4 plus radical 3 times 5 plus radical 3. And the shortcut for the bottom was the first thing squared minus the second thing squared. And now I'll distribute on top. So 4 times 5 is 20. 4 times root 3 is 4 root 3. And then I'll distribute the root 3. Root 3 times 5 is 5 root 3. And root 3 times root 3 is square root of 9. On the bottom, I've got 25, which is 5 squared, minus root 3 squared is minus 3. Square root of 9, though, is 3, right? So if I add like terms, 20 plus 3 is 23. 4 root 3 plus 5 root 3 is 9 root 3. And 25 minus 3 is 22. 23 is a prime number and it's not divisible by 22, so that's simplified. Now, whether they want you to write this as 23 over 22 plus 9 over 22 root 3, who knows? I'm not sure how MATLAB is going to ask it. That's an alternative answer or form. And that's it, all right? R6, R7, this wraps up this section. We're going to do a test on this to see where you're at. And so practice this stuff. We're going to do a test, and I'll let you know, give you some advice after that. All right? Peace. Wow, what a long lecture, huh?